Hello, this is Jack Jackson. We're going to be looking at the derivative today and introducing this fundamental concept. Difference quotient, symmetric difference quotient are ways of getting toward the derivative. And when you're studying introductory calculus, like a Calculus 1 class or a Survey of Calculus class, the study of the derivative and its applications makes up well over half the course. So this is a very, very important concept, and it's important that we get a good start of understanding what the derivative is. So we're going to start with an example that's going to deal with position, time, and velocity. So let's take a look here. And suppose that we have a car that's traveling down the road, and let's say it starts at time t equals 0, and let's say that's noon. And let us also suppose that the speedometer is broken. But the odometer is working, and we have a working clock, and we've got a driver and a passenger. So what happens is the passenger looks at his watch, and every hour on the hour he looks at the odometer, measures uses that to measure the position of the vehicle. Now let's suppose that the positions are distances in miles from a reference point. So for example, these could be the mile markers on an even numbered interstate highway measured from the eastern border of the state. If we go from east to west, from west to east, that those numbers are going to increase. For example, this could be on Interstate 40, measured from the Oklahoma-Arkansas border, and they are increasing. So the car is traveling eastward in the day that we're going to be looking at. So the following table then is going to give us some times and positions. So at time 0 at noon, we get on the interstate in Van Buren, Arkansas at mile marker 7. 1 hour later, we're at mile marker 47. 2 hours into the trip, we're at mile marker 97, and so forth. So a natural question we might ask is, how fast is the car going? Okay. Well, let's first ask, for the whole trip, how fast is the car going on average? Now notice the speedometer is broken. If the speedometer wasn't broken, we could just look down and see how fast we were going by looking at that. Now speed is actually the magnitude of the velocity. Velocity includes knowing the speed and the direction. But in this case, since we're always moving east, the velocity, we can take the speed and just say east, and now we've got a velocity. Okay, so these are, once we figure out speeds, then we just put east with it, we've got a velocity. Okay? So the first question is, what is the average rate of speed or velocity over the total trip? Now, as you're working through this video, I'm going to ask you to pause and consider these questions. Write down what you think the answer is as we go for each question, and then we'll go back over them. So go ahead and pause this right now, work out this video, answer this question, and then in the video we'll go back over it. Pause now. Okay, well, hopefully you decided that that the average rate of speed is found by finding how far we traveled, a distance, a change in position, total distance traveled, divided by the total amount of time that it was. So it's an average rate of change. So we're taking the change in the distance divided by the change in the time. Okay, so let's go back up to our table, and what we're doing is we're looking at from this time to this time, from here to here, for the whole trip. What are we looking at? Well, we're looking at an elapsed time of 4 minus 0 is 4 hours, and we're looking at an elapsed distance of travel distance of 230 minus 7 miles. Okay, so we see that here, 230 mile marker minus 7 mile marker means we went 223 miles. And 4 hours on t minus 0 hours on t means we traveled 4 hours of time. divide that out, you get 55.75 miles per hour. So that's the average speed throughout the whole trip. Now, normally if you're actually driving down the interstate, that may be your average speed, but you're actually going faster at times and slower at times. Speeding up, slowing down, passing cars, slowing down behind traffic, and so forth. Okay, let's look at our next question, and this is going to be really kind of our fundamental question that we want to look at. Okay, so how fast are we going exactly at t equals 2? Well, the answer to that is, well, we really don't have enough information to answer that. But we can at least approximate it. So let's look at some different ways we might do that. I'm going to put it back on the table and have you come up with what you think is your best estimate for how fast we're going exactly at this time right here. Exactly at this time t equals 2. How fast are we going? In other words, what would the speedometer read? Now, we don't know, of course. We don't have enough information. But we can estimate it. Figure out your estimate now. Pause. Okay, now that you're back, let's see what you came up with for an estimate. Now, there's actually several different reasonable sort of estimates we might come up with. And let's look at the first estimate. Okay, is we might actually, one way we could do it is go from time 2 to time 4 and figure out the average speed over that interval. Okay. Well, what would that be? That would be 230 minus 97 would be the distance we travel, miles, divide by 4 minus 2, 2 hours. Okay? See, the details worked out. So notice this is an average velocity. Well, if we say going eastward, it's an average velocity or an average speed going from time 2 to 4, so I labeled it like this. And notice what we're doing is we're dividing the change in position divided by the change in time. We use this Greek letter delta for the difference in position or change in positions, which is the total amount of distance traveled, and the amount of time it took us to do that is in the denominator. Divide, we get 66.5. Now, another way we could do it is we might say, okay, look at this. Instead of going from 2 to 4 on time, go here, right here, between 2 and 3 on the time. And look at their corresponding distances. Let's figure out what that would be. 159 minus 97 over 3 minus 2. There are the details there. Well, that's 62 miles an hour. Okay, which one of those is a better estimate? Which one do we feel more confident about being a better estimate for what's happening right at t equals 2? And why do you think that would happen? Pause this if you need to think about it a minute. Okay, well, if you look back at our table, remember that the 62 miles an hour was based on this one here, and the other one was based on a distance here. Well, since we're interested in what's happening exactly at t equals 2, we ought to get a better estimate if our measurements that we're taking are closer to t equals 2. So we would expect the one that used the 97, the 159, the 2, and the 3, that one's going to be a little bit better estimate than this one that's based on information 2 hours away from then. So we get a little bit better estimate there. So we feel better about estimate 2 than we do about estimate 1 because it is closer to the time of interest. Okay, notice that both of these have the time of interest on the left end of our interval. If we think of this in an increasing way here on the time, the left end here, or the lower time, and then we took a higher time, and of course used their corresponding positions, and then that was for from 2 to 4, but from 2 to 3 it's the same thing. We still left it there. Now, is there any reason why we should always use things to the right here? Could we maybe instead use an interval going out to the left, say maybe from here to here, or maybe between here and here? Well, there's no reason why you should pick one over the other. Necessarily, information about what happens right before the time we're interested in is really about as good as information about what's happening right after the time. So we might use these. So for example, if we wanted to find this one from 1 to 2, we would do 97 minus 47 over 2 minus 1. That's 50 miles per hour. Or we could use from 0 to 2. Of course, the one from 1 to 2 would be a little better estimate. So let's call estimate 3 going from 147 to 297. I subtracted this backwards here. You know, when you're doing a formula like this, it doesn't matter which one you do first on the top, but you have to put the corresponding one first on the bottom. So I did 1 minus 2 and said minus 1 hour. I like to think of it that way because we're going backwards 1 hour from the time of interest, whereas up here we were going forward 2 hours or 1 hour from the time of interest. And when you do that, you're 50. If you go backwards 1 hour, you're 50 miles backwards from where you started. But that still divides out to be 50 miles per hour. You could have done 97 minus 47 over 2 minus 1. It would have been the same thing. So there's our 50 miles per hour. Next question is, which one of these do we feel better about, the 50 or the 62? Remember, we felt better about 62 than 66.5 because this was over a shorter interval. But what about the 50 and the 62? So again, if we look back here, this was 62 miles per hour over this interval, and this was 50 miles per hour over that interval. Which one of those is a better estimate? Well, the answer is we really don't know. There's nothing to tell us why either one would be either better or worse than the other. They're both over a 1 hour interval, including the point that we're interested in at one end of that interval. There's no reason to believe either one of these is better than the other. Now, in actuality, a car could be going down the interstate. It could go fast, it could go slow, it could speed up, slow down. If it runs into some construction or an accident or something, it might even stop completely. So there could be a lot of different things happening. But let's, just for the sake of making this a little simpler for us, let's suppose he's actually speeding up the whole way. And notice that is consistent with this here, because we can think of this as the speeds from each one. Notice that this is 40 miles per hour on the first interval of hour, 50 miles for the next one per hour, 62 miles per hour here, and the last hour is, let's see, it's 1 hour here, 230 minus 159, what is that, 71, is that right? Yeah, 71 miles over 1 hour, 71 miles per hour. Okay, so if you notice, at least the average speed over each hour is increasing. Let's pretend that this car is actually accelerating, positive acceleration, actually speeding up the entire time. I did this in class one time, and one of my students said, yeah, I had a car like that. It took it 4 hours to get up to 71 miles per hour. Okay, but so it's a little unrealistic. But let's say this is the case. Well, if that's the case, what do we know for sure about the actual speed? Again, we're wanting the actual speed right here at time equals 2. Well, if it's 50 miles an hour average the hour before, and it's 62 miles per hour average for this hour after, and it's increasing, the actual speed has to be between the 50 miles per hour and the 62 miles per hour. So that means that the 50 miles per hour is too low, the 62 is too high. What would give us a better estimate still? Well, if one estimate's too low and the other estimate's too high, something in between should be better than either one. Okay, so what we can do is average those two. We know we're between those two, and so we can get an even better estimate, and we can do that by just averaging those two. There's no reason to believe it should be closer to 50 than 62, not necessarily. We don't have any reason why either one of those measurements is better than the other as an estimate, so what we can do is actually just go halfway in between, which is just add them up and divide by 2, the regular old average. So this gives us an estimate for a v average, an estimate for the instantaneous velocity to be about 56 miles per hour. And so this is our best estimate so far. Now let's do one final way of looking at this. Got a bunch of marks here. Let me get a different color pen here. So what if we go from here to here and find the average speed or average velocity from that interval? What would it be? Well, the denominator would be 3 minus 1, which is 2, a 2-hour interval, and it would be 159 minus 47 for the amount of miles that we traveled. I've got that worked out here. We'll call that estimate 5. And so what we have is 159 minus 47 is 112 miles. 3 minus 2 is 2 hours. Divide that out, we get 56 miles per hour. What do you notice about these two numbers here? Well, they're the same, and that's not a coincidence. We can actually prove that. Okay? Now, notice that those 2 points were on either side of our point of interest, and at least as far as the x's go, they were evenly spaced. So they're evenly spaced horizontally. So let's suppose we've got 3 x values, a, b, and c, in order, with b being exactly halfway between a and c. So that would be c minus b is the same as b minus a. And then we have the table a, b, and c, and then their y values, which would be f of a, f of b, and f of c for some function f. Not just the one we have in the table up there, but any function. So we want to find the, you may have recognized this, this is the slope formula that you studied way back in Algebra 1, Algebra 2, College Algebra, all the way through. So we're looking at the change in y over the change in x, that is the y2 minus y1 over x2 minus x1, so that's f of b minus f of a over b minus a. I'll call that the slope using the left interval. So using these 2 points, we get that estimate. Using these 2 points, we'll get this estimate here. That's f of c minus f of b over c minus b. And if we go from here to here, we'll get this. I'm going to call it a symmetric estimate by going symmetrically on either side horizontally of the point B that we're interested in. So that would be f of c minus f of a over c minus a. Now remember, c minus b is the same as b minus a. Now what happens if we average these two here? That means we add them up and multiply by half. So substituting in what we see above, that's f of b minus f of a over b minus a, plus f of c minus f of b over c minus b. But wait, so we need to get a common denominator. But wait a minute, we already really have a common denominator. c minus b and b minus a are the same. So instead of calling this b minus a, I'm going to call it c minus b. So now we have a common denominator, so we can put it all over that one denominator and just add the numerators. Now look what happens. The f of b's cancel out, and we get f of c minus f of a. Now I can take the fraction and multiply numerator and denominator. 1 times the numerator, so the numerator stays the same. I got 2 times the denominator. But think about it a minute. If the distance from, if these distances here on the x's, here and here, are the same, then the distance from here to here is twice as much. So if you do twice one of those distances, you get the distance from C to A, and notice that is our slope there. So it's no coincidence that if you do the slope here and average them, you get the slope from here to here, at least when these are evenly spaced out. So, which of the estimates is the best, and what's the easiest way to do it? The easiest way to do it and the best way to do it was the way that we did it right here for estimate 5. That's the one that's the best estimate. And let's go back and see how we did that again. Okay. Okay, so let me just erase some of this stuff that I have here. And remember what we did. Okay. So we're interested in finding what's happening right here, right at 2. So the best way to get the best estimate was go to the left a certain amount, go to the right a certain amount, the same amount, and take those 2 points, and then just do the good old slope formula, delta y over delta x. And that gave you the same thing as just doing the slopes between these two and averaging them. And so that is our best estimate of this. Okay? And we're going to pick up with this and continue in just a minute.